Hi everybody. I would like to start. For now, I set all of you on mute. If somebody wants to raise a question, please send me a chat. I will have my chat open on my left side. If you don't mind, let's start. My name is Danny Van Gelder. I work for STXI Motion, and I work in the Servo Jive for the last 20 years. I feel a little bit like I'm working in a radio now, speaking to a microphone. I don't see any one of you, but please come and join me for the next 45 minutes.
Hello, Danny.
Hello, hello. Okay. Okay, so today we speak about the power stage that are used in the servo drives. What I would like to talk is to speak about the concept. I would like to speak about the concept, use case to show you some real industrial example, and then to speak about practice numbers. Okay, so the target audience, well, let's say who you are, it's for control and motion application and sales engineers that are working in the motion industry. This webinar is not for hardware design. Okay, if you want to design a hardware, take another flight. I'm not going to speak about the theory. If you go on the YouTube or the internet, there is tons of theory about everything you just think about. The expectation is I will go through the basic concept, show you some real industrial hardware example, and as I mentioned before, we speak about real numbers. At the end, I will give you some idea to do practice homework. If you just listen to me, you might remember 10% or 5%. If you want to learn and take something from here, you must practice and do homework. Okay, the material for this training, there is 2 handout I will show you. And I have some hardware, which I took the picture. Usually when I do it with people, I put the hardware on the table and we go through the hardware. Okay, so let's start. This is a simple servo drive powers for dummies. We learn how to apply wrong AC voltage. No, we are not going to blow up the bus capacitors. I can tell you in every development company, it's happened more than one time that during integration you blow up the bus capacitors. We are not going to connect the AC input to the region. Disconnect the fan. Yes, I did. Now we are working from home. I brought a CDHD, one of the servo drives, and I got some complaints about the noise. So I opened the drive and I disconnect the fan so I can keep working without annoying the other people. Concept. Okay, so I don't know if you got, if not, we can give you later on. There are 2 pages of handout. Usually what I'm doing, I'm printing it out and give to the people. And what we are going to do now is to speak per each section of these 2 pages. Okay, so when I started to work in Servo Drive, I have such a routine. If somebody asks me the same question more than 2 times, I will make a short or a blueprint or a white paper document. One of the first questions everybody asks me all the time, what is the AC input? What is the bus voltage that the motor is seeing? So if we look at regular one phase, we have the L1 and L2. In Europe, in Israel, in Korea, you will have 230 between line to line. This is a one phase. And the servo drive, you multiply it by square 2 to get the V bus. So in our case, we'll have a 300 volt V bus that go into the motor. Now, if you connect three phase, it doesn't matter. All the time, the motor see the square root 2 multiplied by line to line, either if it's one phase or three phase. So in this case, I give example of 208, because if you apply 120 for three phase, here you multiply it by square 3. So here on the right side and also on the hands-out paper, if you see all the relationship, the three most common one are the 160 or 115, this is in USA, 230, or we have the 380, which you have in Europe and USA. Okay, now we go from left to side of the basic blocks of the power supply. So here we apply AC voltage of one phase. The first block where you have in a power stage called the surge protection. Okay, so the surge protection is if you get a spike, let's say in a winter that is more than several times of the AC input, then there is a fuse and the spikes will go to the air and not inside to the power stage. In this case, I protect the power stage of blowing. The next common block is the rectifier. The rectifier take the L1 and L2 and make it sign to one side. Together with a bus, with a capacitor, we make a DC voltage, where on one side we get the B plus, and on the other side we get a B minus. Now, since I don't see you and we are not next to each other, I will ask the question, and for today I will also answer my question. So the first question is, how does a capacitor behave when it's empty? So usually a capacitor when it's empty is like a short. So if I don't do anything, I will get an inrush of 2, 3, and 5,000 amp. So in air conditioning, we have resistors that when it's cold is 1 amp, and when it's hot there is no resistance. So here we have a soft start for inrush to avoid the inrush. So on startup, everything goes through this resistor, which is usually like 1 to 2 ohm. And after 20 seconds, the controller let the current bypass the resistor. Now the next question is, what's happened when I power off the servo drive? So the capacitor still have a voltage. So here I have several small resistors for bleeding. And usually you will see a label on the servo drive say, do not touch the servo drive for 5 minutes or it can kill you or whatever. And that's the reason, because when you turn it off, the capacitor is still full. And it takes time, and we'll see how long it takes to empty the capacitor. Okay, this is just a very quick explanation of what is three-phase bridge. I'm not going through the explanation of the motor. You can find it in many places. What you see here, it's a 2-pole motor, and this is T0. This is the time of 0, where you have here current probe, and you measure the current. and you measure the voltage between one motor phase to another motor phase. So first, you give the bus plus go here and here back, and here you let the bus minus. So here we have 6 switch where every time there is one switch or some of the switches are open or closed, but every phase can be either connected to the B minus and B plus. So this is when T is 0. This is after step 1, 2, 3, 4, and 5. And after one electrical cycle, you will see here the PWM. If you measure between two motor phases, you will see the PWM. And if you measure the current, you will see one sign of the current. Now here we have 2 poles, so there is one electrical cycle per one motor rev. And if we have 4, you will have 2 cycles. So electrical cycle is the number of the motor, the rotor poles divided by 2. But here what I wanted to show you that you have either open switch or closed switch. So we were here, we have a AC line input, we have the surge protection, we have the rectifier, together with the capacitor, we get the B plus and the B minus. We also have in many servo drive today, we have a high bandwidth voltage measurement, can tell me the bus voltage, and I skip the region, we go back to the region, to the three-phase bridge. Now each switch is controlled by the digital with the PWM high and low, U, V, and W. Now the way that we, for example, doing the safe torque off, we apply a 24 volt to the three-phase. And if you don't apply 24, it doesn't matter what the control signal is coming, the three-phase bridge will not be available and the motor will cruise. So each motor phase can be either connected to the B plus or to the B minus. Another important issue is the deadband. Now, usually from physical feature, it takes more time to open switch than close a switch. Now, if these 2 switches are closed, you have a shortcut between the B plus and the B minus. So usually before you close a switch, you give a deadband for the switch to open. Usually in the old days, we used to do it with FPGA, and today everything is programmable by the DSP that control the power stage. The last things I'd like to speak here is about region. So usually I ask where the name came from and why we need it. Now, if the motor decelerate, it start to work like a generator, and it's pump back voltage to the B minus and B plus. So we have to get rid of the extra excess voltage that came back from the motor due to the deceleration. Things about a robot that you want to stop it very, very fast and very strong. So if the voltage reach, for example, 400 volt, this line goes to here, and we dissipate the over voltage, the excessive voltage via external region, and we convert the voltage to heat outside. So usually if you have very strong acceleration, you add external region to your system, and you can look at every user manual where they calculate the value of this widget. Okay, so we see this is the motor. You can see this is the magnet. In this case, we have two pole, like we have north, south, north, and we have the winding outside of the motor. On two of the phases, we put a current sensor, IU, and here we put IW. Here we don't put any current sensor. Now, usually I ask, when I did my study, every time there is an example of a law and how you use it in industry. So I like to ask, which law do you use? Do you use here? So you don't need the third current sensor, and the law is Kirchhoff. Kirchhoff say that all the currents in this point should be zero. So this device is very expensive, so we use only two. And this is calculated because all current here are zero. Once again, it's very important, and many people confuse. If you look at the voltage, it's a PWM. And I will speak about some practice number later, but in this case, it's a 6 amp. We open and close the switches of the three-phase bridge at a 16 kilohertz. If you put a current probe on the phase, you will see a sign. Okay, so we have, this is the frequency of switch, of open and close the switch, and this is the update rate of the software. Some of the common numbers that are used today are 31 or 62 microseconds. People like to speak about current loop bandwidth of 3 kilohertz. Usually it's between 1 to 3, but probably your mechanical system is like 600 hertz or something like that. Okay, like many things, servo drive, the drive is built of two cards. You have the digital card. This is the digital card, where you have mix of motor feedback, field bus, pulse direction. You can have many different kind. Ether card can open, and a power stage, where the power stage is different by the power. So we have the AC input. So we have the L1, L2, and L3. If you understand how we do the rectifier, in our case, you can connect any one phase to L1, L2, or L3. I know with the Japanese, there is a parameter and they do ask you to connect in a specific way. And we have L1 control, L2 control. This is to apply the voltage for the digital board. Most of the drive use the term L1, L2, and L3. There is one drive, as I remember, Sanyo Denki, he used the RST terminology. The next connector is the region. If you remember, we have the B1 plus, and B2 will be connected to the B minus when the FET or the switch will reach like 400 volt. The next connector of the power stage is the UVW. These are the three phases that go into the motor. In the old days, some companies like to use the term ABC. I think it's most common today that most of the companies use UVW. For direction, every company define it different. And you have the PE. Usually small motor does not come with PE, but above like 400 watt, then you must have the PE. This is the STO connector. You can either give 24 volt or you can have a jumper so you don't need the 24 volt. Now the next question, and again I will be the one to answer that because I speak for myself, will be which component fell first, or usually if you do the MTBF, usually if you do MTBF, it's theoretical. You take all the component and you do some calculation. Which component fell first? So theoretically, the first component to fail is the fan. In our case here, we use a 12 volt with a 13 CFM. Oh, somebody's in the toilet. I mute everybody now. Everybody, we get more and more people. It's exciting, but I have to put you on mute if you don't mind. So the first component to fail is the fan, theoretically. Usually I can tell you from my hard experience that some bugs will make you hard time before your fan will fail. And the fan will fail after many years. Maybe you will be in another place. So in normal operation, what we do, we work at a quarter of the power needed. And only when we reach 60 degrees, 60 degrees is the first threshold of the warning of temperature, then we work at full power of the fan. So that's a nice design of our engineer. His name is Oren, to expand the life of the fan. Where is my... Okay, I will go very briefly. Here are all the faults that we have in a power stage. We have overvoltage. If you don't use a regent or your regent is not properly designed and the bus go above the voltage that it can carry, he will stop and tell you an overvoltage. The first, when I started to work, the first error every time I get from a new customer is this one. It's happened many times that the customer connect the logic and then he say the drive doesn't work because you get an undervoltage. Look at the 7 segment, you get a small u, and make sure that the L1 and L2 are connected. The most severe warning is the power stage fault, overcurrent. Overcurrent means that there is a short between the B plus and the B minus. Now, since we don't know what's happened, we are not allowed you to reset this warning. We ask you to recycle power the servo drive and ask you to find out what's happened and why you have a short between the B plus and B minus. So this is the only fault. I speak for our drive. It's a little, let's say all the servo drive do the same. They're all running motors and they all have a very similar fault. Just the behavior might be a little bit different. The next one is STO. So if you don't have an STO, it will tell you, I don't have an STO. Either put the jumper or give me the STO. Or there is an STO, so you are not allowed to run it. Okay, now if you remember in the handout, I go to page number 2. So we have the bleeding. As you remember, the capacitor, and now I turn off the servo drive. And I have to the capacitor is full. So actually, if you look at the time, it's the V bus exponent of the bleeding resistor and the V bus capacitor. So once I asked the engineer how long does it take, and the number that you are looking for is the 60 volt. Under somebody want to say something? Okay, so under 60 volt, it's safe. So this is Excel spreadsheet I did from a real, this was a CD many years ago, where I took the
audio goes in and out.
Yeah. Okay, I mute all. And if you look here, it's take about 220 seconds to discharge the capacitor. And that's the reason that you will see always on the label of servo drive, wait 5 minutes. If you look at some European, it's tell you that it can kill somebody. So that's the time for discharge the capacitor. I show here the flex cable. Usually the power stage and the digital are connected with a flat cable where all the information is the PWM, high and low, VBus information, the fan speed, and the actual current measurement. So these are all the interaction between the control board and the power board. Just to mention, there is one more feature. It's not the power stage, but it's important to know. It's the fallback. Usually, as an engineer, you select a stronger servo drive than the motor, but you have to make sure that the servo drive will not burn your motor. So there are several ways to protect it. We use something called fallback. After 2 seconds of peak, we force the current to go down. Maybe I will. Any questions so far before I go to the following handout? Okay, I mute everybody. So the second handout about power stage is related to temperature. So it's either you got it. If not, contact either me or somebody from STXI to get a PDF. Okay, so we have several temperatures that we read from the servo drive. We have the control board, we have the power, that's the PCB, and we have the IGBT. So usually we have first a warning, usually at T, which is smaller than T1. And when we have the IGBT, then we stop. Usually the temperature of servo drive, the first warning is 60 degrees. Then at 80 degrees, usually we stop the drive. And we don't allow the heatsink of the servo drive to be more than 100 degrees. So it's very simple to remember. Servo drive must be below 100 and working below 80, where motor can work up to 150. So these are the area where we work regarding the temperature. So where do we measure the temperature? So we have first, we have the junction inside the PIM or IPM, and this has to be below 120 degrees. And here, this is where we get the information of the power module, power stage. This is the OT2, and on the power stage, usually we have a temperature sensor, and we also make some measurement of this delta, and we don't want the drive to run, let's say, more than 60 degrees, and the heatsink or number one work of the heatsink is to cool the three-phase bridge, which can be either MOSFET, FET, IPM, or PIM. I hope by end of this webinar, at least you will know the abbreviation of each one of these. So far I spoke about basic concept of a power stage. Now I want to skip and go and show you some real industrial example. So that's what I call use case. Okay, so usually what I'm doing, and I do it for many years, I put this power stage on the table and I ask people, where is L1 and L2? So once again, today I'm the one that asking the question and answer. So I will show you here. It's L1 and L2. That's where I connected the AC input. Where are the surge protection? So the surge protection are right away next to the input of L1 and L2. It's like a fuse. If I get a spark like from outside, then he take it to the PE. So in this case, we have only a servo drive of one phase, and you see two surge protection. Okay, the next question is, who is the V-bus capacitor? You remember, so these are the two bus capacitor. It's very important also to see the plus. It looks okay. If there is a problem with a plus, then either the capacitor dry out or there is another fault of the capacitor. So this always, when you look at the servo drive, the big capacitor are for the bus voltage. Soft start. Okay, the soft start, you see here there is a relay. So when the drive is cool, so the relay is open, so everything go through the resistor of 1 ohm, and after like 20 seconds, the relay close and the current can bypass via the relay. IGBT. This is the IGBT. Inside, in this case, you have also the rectifier and the three-phase bridge. All the switches are here inside. So things about 1, 2, 3, 4, 5, 6 transistors. Okay. On one side is the bus plus, and on the other side is the bus minus. And every one motor phase go through these sensors and here out. Another one go through these whole sensors and out. And the three go without whole sensor to the IGBT. Now these are the gate drives. So the control board send a PWM to the gate drive, and the gate drive open and close the switches of the IGBT. And here I already mentioned these are the current sensor. And the last things is the STO. Things about yellow area. This is the STO. And here we operate the IGBT, and if we don't give it 24 volt, the IGBT is dead. So if you can look here, the main or the most expensive devices are the IGBT, and the Hall sensors are also very sensitively to the, let's say in Pareto, the price is a little bit higher. Okay, I just look at the other side of the power stage. So I can look here. I see this is the bus capacitor. And here I have the bleeding. That's the bleeding resistor. So when you turn it off, you discharge the capacitor from here, and it takes like 220 seconds. Here you see more gate drive. In this case, we don't use a fan. So here you can see the L1, L2, and this is for the control board. And here you can see the UVW and the regent. So here you have the B plus and the regent. So it's your call if you want to connect external regent, yes or no. This is just a good picture. I said I will edit. You can see the nice writing here. So L1, L2, spike, the IGBT you can see here. You buy the IGBT. This is the Hall sensors. this is where the flat cable go to the control board. So it looks very simple, but it's not. I don't know many engineers that do power stages. Let me see how. Any questions so far? Anybody want to ask questions?
בינתיים לא.
Okay, so as I told you, many of the book mount, okay, that's what I call book mount. It's the servo drive you put in a machine, has a control board, heatsink frame, and the power stage. Here you can see the heatsink. That's the control board, and that's the flat cable. The only information mainly is the PWM to UVW and the whole sensors back. This is the fan. Usually for fan, if you want to decrease the footprint of the servo drive, you add a fan. There are pro and con for fan, we'll speak later. In this case, now I have to ask which direction the flow goes. So usually the flow go on the writing. So in this case, we take air from outside and send it inside here, and then it's go here outside. And the three-phase bridge is underneath here, and that's it's a very good method to get rid of the heating of the three-phase bridge. Okay, now we look at another servo drive, another industrial example, which I'm very proud of it. I was part of this project. In this case, we use FET. So the DC input, it's here. Here you can see the V-bus capacitor. And here you can see 6 screws. So these are 1, 2, 3, 4, 5, 6. You remember 6 switch are controlled by the middle leg, and these are FET or MOSFET, because this drive is 100 volt. So in 100 volt, you usually use a MOSFET. Okay, so far I just show you 2 use case, industrial example, one of a book mount servo drive that get one phase 230 or 110, and the second was a custom drive that get 100 volt for a medical application. Now, what I would like now, we have another 20 minutes to speak about real numbers. Okay. So first, you can see here it's example of one phase. So the bus voltage to the motor is 320. Usually when I show it to people, I ask them what is the AC input. So I expect them to divide it by square 2. One time I was in Taiwan and it was 160. And I asked, hey, what's going on? And then they told me that in Taiwan, at the same room, you can have a 110 plug or 230. So in this case, we were connected to the 110. Here you can see all the numbers of the temperature of the control board, the power board. Here you set the over voltage threshold, and this number are peak. If you want the RMS, you have to divide it by square root 2. Okay, now this is I call the big matrix, or the worldwide matrix. This is the most common input. We have a DC, usually from 24 to 100. We call it low voltage. And and you just give a plus voltage and minus. Then we have the second group, which we call, some places call it the medium voltage. You can have either one phase or three phase input. This is L1, L2, and this is L1, L2, and L3. So if we look here, one phase, 230, in Asia, they call it 200 volt drive. In Germany, they call it 300 volt drive because they are looking at the V-bus. In Asia, they look at the AC input, and all of them say the same. Now we have the three phase of the high voltage. So we have either 380, this is what we have here in Israel, in Europe, in China. And don't forget, if you design a high voltage and you take it, you bring it to USA, they give you a little bit more. So don't forget that your chest should be good also for 480. In Asia, they call this family 400 volt. In Germany, they call it 600 because the V-bus is 600. So if a Germany tell you a 300 drive, you mean this group. If somebody from Asia tell you 400 volt drive, he means this group. Now, this is not science, but from my experience, you go from one phase to three phase once you reach 750 or 1 kilowatt. Usually I ask why, and I asked why, now I'm also answer. When you go above 1 kilowatt, the ripple, the small ripple on the capacitor might be too high. And if you go to three phase, the ripple on the current ripple is low. So to extend the life of the voltage capacitor, you have to go from one phase to three phase. DC is usually battery application, medical application, where they want to be below 60 volt, application like that. And we see more and more like AGV and many medical, all medical, they are trying for, because of certification, to be below 42. In Asia, the 200 volt, the one phase, 200 volt, is the most common, the 400 watt motor. It's a one phase, 230 with 2.8 amp RMS. So this is the most, I think it's the most common axis in the world. In Europe, they like the high voltage. They like the high voltage and they like a lot of safety to make it difficult to everybody. In USA, you will find 110 volt AC, 208 volt AC, and 480 volt AC. So if you probably during your life heard either 100, 300, 600, this table tell you where you are, if you are low voltage, medium voltage, or high voltage. Okay. Now the main component in the power stage is the three-phase bridge. You can have either MOSFET or IGBT. Now MOSFET is good for high current, but low voltage. They have low RDS resistance, and the frequency of open and close is very, very high, and it's a simple gate drive. You can go with PWM switching 8, 6, and 32, also 64 and 128. If you look at this diagram, this is the voltage, where here it's like 160 or 120. This is MOSFET. This is IGBT, and this is BGT. We don't use it in our servo drives. So the IGBT is when you go above 200 volt. It has a low speed of switching, but 50 kilohertz is good enough. Usually you will see PWM or switching of the IGBT of 4, 8, or 16 kilohertz. Nowadays, we used to have IPM. IPM was a three-phase bridge, above 400 watt. Today, you can buy the rectifier plus the three-phase bridge for 100 to 400 watt servo drive. So if you look at a drive of 1.5 amp or 3 amp, it will have an PIM. All the biggest one will have an IPM. So if you remember the custom industrial example I show you use MOSFET, and the servo drive use the PIM. Now higher PWM give you better performance, but it's get hotter. If you have a very low motor inductance below 1 millihenry, you probably have to go even high to 32 or 34 kilohertz. The most common switching of the three-phase bridge is 16 kilohertz. It's all the drive that goes up to 1 kilohertz, and the motor inductance is between 1 to 10 millihenry. If you go above 1 kilowatt, you probably go down to 8 or 4 kilohertz of switching the three-phase bridge. Now, maybe one day there will be also the technology of GaN. I don't know if you heard about it. We at Servotronics, we made one like 2 or 3 years ago a servo drive with a GaN switching. It has the best performance, but it's too expensive at the moment. Okay, so now I'm speaking about the fan. So what is the fan direction? So as I told you, it's take the air from outside, inside, and it's going here outside. The Pro, it allows smaller footprint. The Cone, it's the first component to fail. Small drive up to 200 watt is without fans. Medical and also fab don't like fans and ask you to design a servo drive without fan. Current sensor. First, you have a current sensor in open loop, closed loop. They are very, very important for the performance. So you need 14 or 16 bit. It's a quite expensive device, so people try to find all kind, but if you want good servo performance, you must have a very, very good current loop. It doesn't matter how much you are good in algorithm. If your current loop is not good, you cannot compensate it in velocity or position. Now my printer is starting to work. Okay. Processor of three-phase bridge, just again speaking about worldwide. Servo drive from Asia, usually they like to use FPGA to do the current loop. It's very fast, but it's not simple to make change. In Israel, we like to do algorithms, so we use the DSP to do the current loop, and we can do a complex algorithm. Let's say like 30 years ago, the first three-phase bridge algorithm was 6-step. Then it was three-phase, when every phase is 120 degrees from the other. Today, I believe most servo drives do the DQ control of the Parker conversion. So you use only 2 vectors and you can do it much faster. Remember all the time, motor drive current loop parameters are measured by a dyno and are factory setting. You as a user should not do anything with the current loop parameters. They are only derivative from the motor parameters and the electronics of the power stage. Here are some typical numbers of the update rate of the processor. So I will say that we have even today drive can do even 31 microseconds, 32 kilohertz. A very common one is a 16 kilohertz, and medium performance, I would say it will be 8 kilohertz. That's the update rate of the processor to do the current loop. And usually velocity is half of it, and position is half of the velocity. Just to speak about the bandwidth, bandwidth is you measure the current divided by the command. If it's below 0.7, it's mean that there is no response anymore of your power stage. So usually you measure it at, let's say you have 10 amps, so 10%, at 50%, and 100%. So, and you send the sinus signal. So here you can see that the command in blue and the measure are going together. Now here you can see it's when it's 0.7. So you have a command, but the power stage cannot follow the signal that's coming in, and you reach the bandwidth. So here you have example of a custom drive. So small signal, it was at 1300 hertz, it start to go below 0.7. Medium signal was 700 hertz, and a large signal was 400 hertz. So that's a very simple way to measure your bandwidth of the current loop. Usually people say 3 to 5, but as I mentioned before, your mechanical system probably will be below 1 kilohertz. Okay, I have only 5 minutes and we got to the last slide. If you want to take something from here, you have to practice, do some homework. So here are some suggestion homework for you. The first one is you can measure the V-bus with a voltmeter. Be careful, it is a high voltage, it's very dangerous. I assume you are electrical, you know what you're doing. And the only way to understand how the V-bus looks is to measure it. You can take a current probe and measure one of the motor phase in continue, and also you can lock the motor in stall and see how the current behaves. Finding the bleeding time. So contact your servo drive manufacturer, ask him what is the resistance and what are the cap value, and calculate how long it takes you to reach 60 volt. Another one is run your motor in current loop only, and figure out what is your maximum current that you can hold with the motor with the hand. Find out what is your fan, what is the CFM of the fan, and what are the over temperature of your servo drive, which probably will be 60, 80, and 100 or something inside between this. This is pretty much what I wanted to tell you today. I hope something, and I said all of you are unmute.
Thank you, Danny.
Let me know if you have any question. Okay, so thank you very much.
Thank you.
See you on the next webinar.